Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll solve a problem on centrifugal pump. Even in our last lecture also we have discussed a problem on centrifugal pump, but this problem is slightly different than the previous one what we have solved. So here we have taken the question of a centrifugal pump. A centrifugal pump is having outer diameter equal to 2 times the inner diameter. So your diameter value is not given, but it mentioned that outer diameter is equal to 2 times of inner diameter, and it is running at 1000 rpm and works against a total head of 40 meter. The velocity of flow through the impeller is constant. So velocity of flow through the impeller is constant. Vf1 is constant and equal to 2.5 meter per second. So this is velocity of flow, that means Vf1, and Vf1 and Vf2 both are equal here. Okay, and the vanes are set back at an angle of 40 degree at outlet condition. Okay, if the outer diameter of the impeller is 500 millimeter and width of outlet is 50 millimeter, determine vane angle at inlet condition, work done per second by impeller, and the manometric efficiency. So in the last problem what we have discussed, there we have not calculated the efficiency value, just we have calculated the work done per second per unit weight of by the impeller. So for this problem I have taken already the diagram from the book. So anyway, this is the simple one. This is the vane, or we can say this is the this is vane, or we can say the blade of the pump, and this is the inlet velocity diagram, and this is the outlet velocity diagram. So the inlet velocity diagram, as we can see, this one already have discussed previously how to draw the inlet velocity diagram for the pump. Okay, and this is theta. Theta is the angle between this tangential velocity and the velocity of flow. Okay, or you can say theta is the angle theta is the angle between the relative velocity and tangential velocity. Here actually alpha is to there, which is 90 degree, and Vw1 is 0, and this is about the outlet velocity. This is outlet velocity diagram. This is outlet velocity diagram, and this is inlet velocity diagram here. Anyway, this velocity diagram already we have explained previously. Again, also if you want to see, you can see the previous lecture, or else you can see in the inlet condition, this is V1 equal to Vf1, and outlet condition, our V2 will be this one. This is absolute velocity to outlet condition, and the Vf1, that Vf2, that is the flow velocity. Okay, that will be perpendicular, and this will be our angle. Okay, here phi is there, and here we'll get the value of beta, suppose, and this is the field velocity at the outlet condition, and this is the tangential velocity whole we need to consider, because this is the outer diameter, and here this is the tangential velocity at the outlet condition. So this is U2. Anyway, so these are the information regarding the velocity triangle at inlet and outlet condition. Now come back to this problem. Let's see what are the first we'll see what are the data given, and what we need to calculate. So at the initial stage we can see the diameter of this is given, but it's running at 1000 rpm. So diameter, outer diameter is not given. Yeah, outer diameter is given, already given here in this middle. So that one we can write. Suppose if you write outer diameter, we used to mark it as D2. So outer diameter, this is nothing but D2, which is given 500 millimeter. 500 millimeter, and that one we can convert into meter. So we'll get here 0. This is 5 meter. Similarly, in the first line itself is given the centrifugal pump is having outer diameter equal to 2 times the inner diameter. Then inner diameter also we can find out from here. As per the statement, we can write inner diameter, which is denoted by D1. This one we can write 2 times of this, means this one, then this will be half. So half in the sense 0.5 divided by 2. So we can write this is 0.25 meter. This is our inner diameter. Now it works against a total head of 40 meter. So this total head of in the 40 meter is nothing but that we need to consider, that is head H, or we can write manometric head. This is 40 meter. Okay, the velocity of flow through the impeller is constant. The velocity of flow, this one, the velocity of flow through this impeller is constant. That means Vf1 and Vf2 both are same. So velocity of flow Vf1 we can write is equal to Vf2 is constant, that is 2.5 meter per second. Okay, the next is the vane angles set back at an angle of 40 degree at outlet condition. So at outlet condition, the angle, vane angle is this one. Okay, that's phi. So let's consider phi equal to 40 degree. Okay, and yeah, width is given. So here one more value is given, width at the outlet condition. That means width we used to mark it as a B. At inlet condition V1, at outlet condition V2 we can write. This is nothing but 50 millimeter. And again we can just write it into meter, 0.05 meter. So these are the data are given in the question, and what we need to calculate, first one, the vane angle at inlet condition. So for the vane angle at inlet condition, if you see, the vane angle at inlet condition is nothing but we need to find out the theta value. Here phi is given, we need to calculate the theta value. So theta, how we can find out in this inlet condition? So let's write vane angle at inlet. So at outlet condition the value is given. So at inlet condition, so here in this triangle, if you see, we can find out like we can write this by seeing this triangle, we can write the formula like tangents. We can take the value of tan theta. Here we can write the tan theta equal to, so here the hypotenuse is there, base is there, and this is perpendicular. So we can write here yeah, hypotenuse perpendicular by base. So here we can write this is Vf1 by E1. Okay, so Vf1 value is given 2.5 meter per second, and E1 we need to calculate actually here. Okay, so at the starting of this we need to calculate the E1. E1 is nothing but the tangential velocity at the inlet condition. So tangential velocity at the inlet condition, so you can calculate here we need to write yeah, so E1 we know the formula, this is pi d1n by 60. Similarly U2 we can write this is pi d2n by 60. So in these two, only difference is d1 d2, only diameter is difference, remaining all are same. So what I'll do, pi into d1 is nothing but 0.25 into n. N is how much? N is 1000 and divided by 60. So here how much I'll get, I can just twice this value here, because if you see this is pi into 0.5 into 1000 and divided by 60. So here we can write this is 66 con, and this one we can write 3, and this is 50. So we can just calculate this value, how much is there. This is pi into 0.25 into 50, and this is divided by 3, 13.09. So this one I can write, this is 13.09 meter per second unit. If this is 13.09, this one obviously we can double up, this will be there. So you can write this is 26.18 meter per second. Only this diameter is changed, twice of the diameter, remaining all values are same. So we can put the value of here 13.09. So we can find out this value tan theta. So you can write here theta equal to, we can write 10 inverse. Here we can write 10 inverse. How much this value will come? That one we can write. This is 2.5 divided by 13.09. So again we need to find this value. This is 2.5 divided by 13 point. This is 09. This much, and 10 inverse of this, that is 10.8. This much degree is there. So here we got the value theta equal to 10.48 something value is there. This is the vane angle at inlet condition. Okay, first answer we got it. Now the second answer, second question is given work done per second by the impeller. So work done per second by the impeller, this one is little bit lengthy, because we know that we know the formula, that is yeah, for this actually work done per second by the impeller on water per second. So this one we can write, this is nothing but W by G into VW2 U2. Okay, this one we can write this equation which was already derived previously. We can write from that. Okay, now actually W we can write here. W we can write here, the value of W we can write, this is rho G Q, and already G is there in that denominator, and here it is VW2 U2 is there. Now G will be cancelled, so what will be there, like rho Q, VW2 and U2 will be there. These are the values are there here. Now in this equation, if you see which is the unknown here, unknown part is only VW2, remaining values are known to us. So you can write here like 1000 into GG cancel already, and this is U2. Yeah, here okay, Q value we have not identified till now, correct. One more missing is there, that is Q. So here I'll do the, here I'll find out the value of Q. Q is nothing but the discharge. So discharge, how to calculate? So we know Q equal to area into velocity, AV. So here area equal to that is impeller area at the outlet condition, that is nothing but pi D2 and B2. Okay, pi dB, pi into diameter into width. So at the outlet condition we are taking, that's why you can write pi D2 B2 into, with the velocity, what velocity is nothing but VF2, the fluid velocity. Okay, now pi value is there, diameter D2 how much is there, 0.5, and this is, next is B is 0.05 given. Yeah, B is 0.05, and VF2 also we have already identified, because VF1 and VF2 both are same, and I hope already is given in the question. So you can write this is how much, 2.5. Now we need to find out the value of Q. So what I'll do here, let this is pi into 0.5 into 0.05 into 2.5. So we got here 0.196. This is the discharge. So I can write the value is Q equal to 0.196 meter cube per second. This was volume of water per with respect to time, second. Okay, now we can put the value here. So 1000 here, 1000 into densities of water is 1000. Now Q is 0.196, and into VW2. So VW2 we have not calculated. U2 value already calculated. So you can write this is 26 point, this is 18. Okay, let's keep this value as usual. Now we need to find out the value of VW2, so that I can write here, this is work done by impeller, on water per second. Water per second we can write. Okay, now how to calculate the value of VW2? This VW2 value is the outlet condition, how to find out? So again, for this we need to consider outlet velocity triangle, and we can calculate, like if you take the again tangential cosine, that means by tracking this right angle triangle, if you write the formula of tan theta, here it will be tan phi. So at the outlet condition, we can write tan phi. From the outlet velocity triangle, we can write tan phi equal to, this is similarly PF2 divided by, this is perpendicular is there and this is the base is there. Suppose the base is how much, that value we don't know. So what we can write, u2 total length minus this length. So then if you write in this way, u2 minus vw2, then vw2 is unknown, there we can find out. So what I'll write here, this is u2 minus vw2. Now if you see, tan phi value is given in the question. So what I'll write here, I'll write u2 minus vw2 equal to vf2, how much, vf2 already given in the question, this is 2.5 divided by u2 is nothing but 26.18. Sorry, here I have already taken reversely, correct? So yeah, here I'll write the value of tan phi. So tan phi is nothing but tan 40 degree, correct? Now again, what is we required here? We need the value of vw2. So I can write vw2 is nothing but, I'll take this value this side. So u2 is how much? This is 26.18 minus, I can write this is 2.5 divided by 1040, correct? 1040. So we can find out the value of vw2, and finally we'll put the value there. So here what I need, just with the help of this calculator, we'll do 1040. 1040 means, now we'll do one thing, 2.5 divided by bracket start 40 trigonometry 1040 and again equal. This is 2.979. If you see, this is 2.979. That means this 26.18 minus 2.979. If I minus this one, obviously I'll get 26 minus 24, 2 minus 20, that is 24. So this 0.97 is there, mean 23 point something I'll get. So this is what I'll do, minus 26.18 I'll do. So I'll get 23.2. So the same thing I'll write here, 23.2, and this is meter per second. Now we got the value of vw2. Now this value we need to keep it in this equation, correct? So now again, what we can write, work done by the impeller per second is equal to, this is 1000 into 0.196 into, this is 23.2 into, this is 26.18. Finally we'll get the value now. So what value I got here, just I'll multiply in this. This is 1000 into 0.196 into 23 on next 26.18. So we got the value of 1,19,048. Anyway, what value we got here, same thing we'll write here, that is nothing but 1,19,48. 1,19,48. So this is the value of work done per second, by the impeller on water. And this you can write, this is Newton meter per second. Okay, now the last one is nothing but, that is efficiency. Okay, so efficiency, manometric efficiency need to be calculated. So manometric efficiency, the formula is for this, you know, this is GHM by Bw2 U2. So if I see this formula, like simply we can put the value 9.81. HM value is given already, manometric head, and this is divided by Bw2. Just now we got the value 1,19,048 into U2. U2 is how much? 26.18. So finally we'll get the value of manometric efficiency. Let's see how much we are getting. So this one, I'll make it 0 now. In the numerator, we have 9.81 into 40 and divided by bracket start. This is 119 and 048 multiply 26.18 bracket close. We got this is 1.259 392, correct? 392 divided by this much is there. Yeah, correct only. Okay, so here VW2. Okay, VW2 is not this is okay, this is the work done actually. I have written the work done value here, sorry. So we need to write, yeah, here we need to write actually. Anyway, let's make it 0. So this one, the value of VW2 is nothing but this is not. We need to write 23.2 actually. So I have written the work done value here. That's why it came differently. So again, I'll write 9.81 multiply 40 and divided by bracket start. This is 23.2 multiply 26.18 bracket close. 0.646. So now we got the value, efficiency value. That one we got 1.25 something, 10 to the minus value is there. That is different. So anyway, 64.6. So here I can write this is 0.646 or equal to, you can write this is 64.6%. This is the efficiency value. Okay, this is the manometric efficiency. So like the only we need to solve the problem in the centrifugal pump. Any kind of problem is given, first of all we need to focus like what are the data are given and how to draw this velocity triangle. So velocity triangle is very important. Okay, once you understand the velocity triangle, it will be easy for you to solve the problem. So at the starting stage, just try to identify what are the data given from the question. Okay, and but before that you need to at least clear about the concept regarding that centrifugal pump, what is centrifugal pump and how to find out the work done, how to find out the efficiency. These are the information at least you should have so that you can easily solve the problem. I hope you understand this problem. If you are having any kind of doubt and query regarding this, you can give a comment on the comment box. Thank you all.